So, welcome everyone. It's so really nice to see you here today. I'm Anna Rutgersson. I'm Professor of Metrology at the Department of Earth Sciences here at Uppsala University. And I'm really happy and proud to welcome you all to this, for us, really big and great celebration. Today, planning today has been a true challenge. We have encountered the pandemic and also a big lightning strike, killing all the sound in this amazing venue. So, due to those difficulties, we have not been able to have, we are not able to have our first speaker, Professor Phil Jones, here. And we are really sorry about that, and I know he's really sorry about that. And due to these sound problems, we cannot have him digitally either. I know he's listening, but we cannot get the sound back, so we will not be able to hear him talk. So we have a recorded presentation from him, and he also says that if you want to ask questions, you can send an email to me, and then we can try to solve it at the end of today, if it's possible. But we are really sorry about this, and he's really sorry about this. But still, we will be able to hear his presentation. So I will give the word to our moderator today, Associate Lecturer Conny Larsson, who has a long history here in Uppsala, at Uppsala University as well, and he will take care of us during the day with his confident hands and voice. So please, Conny.
The weather has already celebrated the 300 years celebration with thunder and lightnings around a week ago. A lightning strike down destroyed some of the technical installations in this fantastic theater. We can't use some parts of the sound system with microphones and speakers in the floors, walls and ceilings. But I know that the acoustics is very good even without the whole sound system working. Therefore, we have to use different types of traditional microphones. And this one is for the recording. Now over to today's topic more. Uppsala has one of the world's longest series of weather observations. The observations date back to the 12th of January 1722 by Professor Erik Burman and the young Anders Celsius. Every day they went outside to record the temperature and wind direction. And hopefully, I think, inside they recorded the air pressure. Over the years, many different people have contributed to the data series. And on the 12th of January this year, the series had become 300 years long. In August 1975, I myself started here doing weather observations as a part of my work as an assistant. So I can answer for some parts of these points up there between 1975 and 2017. After this short introduction, I would like to give the floor to our Vice-chancellor at Uppsala University, Anders Hagfeldt. Please.
It's a pleasure to be here finally, and just before I start my speech, to personal connection to this, my teaching topic has been over the years thermodynamics. So of course you mentioned Celsius and connection between heat and temperature and why water is chosen. So that has been a big pleasure actually to have these topics to teach with. The second connection is that I invented weather in 1986. I had as a summer job in my hometown Norrköping at SMHI the task to fill in what had happened was that I worked at the climate section. And recently at that time, this is 1986, SMHI had put up 12 computerized weather station in Sweden, and they collected weather data every 3 hours, I think. Now at that time, computers hanged up quite often, so there was a lot of gaps in the data which I had to fill in. That was my summer job. So I told my parents that I invent weather, and that's what I'm doing. Dear colleagues and friends, veritas naturae, truth through studies of nature. This is one way to translate the words in the middle of Uppsala University's seal, under the sun. A splendid example of a person who was animated by the belief that this motto is the path to knowledge is Anders Celsius. And let me elaborate. Gathering here today, many people will talk about the series of temperature measurements, as Connie mentioned, that Professor Erik Burman started with assistance from Celsius. It was here in Uppsala, and of course that is one of the pillars on which we base our knowledge of all those statistics that relate to heat and coolness here in the Nordic region and on Earth. However, I would like to concentrate on another side of Celsius. And here I should thank Professor Bo Sundqvist for information. And the reason I chose this topic is that it reveals so much about the conditions for science and the forces that motivate a scientist driven by curiosity and the need to find answers. The forces that motivate all of us who have tried to prove theories or who have sought answers where there were none. In the 1730s, Celsius arrived in Paris. He found himself in the midst of a debate about the planet Tellus and shape of this, our Earth. Jacques Cassini, a specialist in surveying, had concluded that the globe was probably shaped like a lemon. His theory contradicted Newton's ideas, which assumed that the Earth appeared flattened at the poles, more like a tangerine. And what was the truth? The French Academy decided to send an expedition. Measurements would be made in Ecuador and France, and the project would be funded by the King of France, Louis XV. The tangerine faction, as we may call it, was led by the mathematician and philosopher Pierre-Louis Moreau de Maupertuis. He wanted to supplement the measurements of degrees with a control from a place far to the north. As a result of conversations with our man Celsius, the place chosen was Tornedalen, in the far north of Sweden, which Celsius' grandfather had visited with King Charles XI to observe the midnight sun. The expedition set off in spring 1736. The team appointed to make the measurements and calculations consisted of 4 members of the French Academy of Sciences, a corresponding member, a secretary, a draftsman, and Celsius. They stayed in Tornedalen for a year, measuring and checking. One of Celsius' students, Anders Helland, who came from Tornedalen and spoke Tornedal Finnish, meänkieli, joined the group to assist in contacts with the local population. There are some stories, but we can say that the whole enterprise made a positive impression locally. The measurement showed that it was Newton who was closest to the truth. Cassini of the lemon theory argued at first that the measurements were inadequate. He cried fake news, but he soon conceded. The ambitious project to find the truth through careful study of nature had borne fruit. The Earth is shaped like a tangerine. With these words about one of our forerunners and inspirations, I would like to wish you welcome here today. And if any of you would like to read more about Celsius, let me take this opportunity to recommend a book by my predecessor as Vice-chancellor, Bo Sundqvist. Anders Celsius och Skådetornet. Do read it if you have a chance. I can really recommend it. And I have heard that it's being translated into English, and the title might be Anders Celsius and the Observation Tower. With these thoughts, thank you very much and very welcome.
Thank you very much for this presentation, this introduction. Well, now we continue with the program. And the next speaker is, as you heard Anna talked about, is Phil Johns. He is a professorial fellow at the School of Environmental Science at the University of East Anglia. And his title is The Celsius Temperature Series in a Global Context. I'm going to say some more words. I hope that Phil is watching us. So hello, Phil. Welcome. And sorry that you couldn't make it. And he is a former director of the Climatic Research Unit and a professor in the School of Environmental Sciences at the University of East Anglia, with an extensive work on the use and development of temperature records. We are very proud and glad to have Phil give the introductory presentation for our Celsius Symposium. Unfortunately, COVID delays prevented us from having Phil here in person, and the thunder and lightnings here prevented us to give him the opportunity of answering questions. But I'm sure he is watching. So let us start his presentation.
Hello, everyone. Hello, everyone. Today I'm going to be talking to you about series with long temperature records in Europe, and also briefly at the end, some global temperature averages since about 1850. It's going to be a bit of background at the beginning about instrumental observational issues, exposure, and urbanization issues, all potential problems with long-term recording of temperatures over many centuries. And these are issues with long European records. And I'll highlight some of the possible issues with Uppsala. Towards the end, we'll get to global temperature averages and the robustness of that record. I'd like to acknowledge help from Michael Taylor, who's in crew for some of the diagrams, and some old plots from Anders Moberg, who I used to work with a long time ago. They're both acknowledged. So some of the background terms. What we want to know about a site is the station history or metadata. So this is what is known about the site, and observation time changes and changes to the instruments and methods of calculating daily and monthly averages. For Uppsala, you're going to hear more about that this afternoon from Hans Bergström, and details of that are in a 40-page paper in Climatic Change from 2002. Now, allowing for all these issues is often referred to as homogeneity, and sort of making consistent records through time. For Uppsala, there is good metadata, but we only have what was written down. Issues will have happened which weren't thought important at the time, so we've always got to remember that. Now, in terms of potential biases, these are things that may affect more than one station. And so by intercomparing neighboring stations, they may all be similarly affected. This may be due to exposure issues with the introduction of screens at the same time by a Met service, or urbanization, where the towns like Uppsala and Stockholm might be similarly affected by the growth of the town or the city itself. And they're both unlikely to be adjusted by homogeneity algorithms because maybe stations nearby will be similarly affected. Now, no site of more than 50 years record really is free of problems. And most of these numerous issues are not just site moves, but there's other issues too. The rest of the talk is going to discuss ways of dealing with these and their potential effects on long time scales. So homogeneity is this word we use for long-term consistency. And it was realized that there were problems with this in the 17th and 18th century. And these were allowed for in the 19th century. This was mainly by taking measurements for very short periods in high detail in every hour, for example. The whole concept of homogeneity was defined by Conrad and Pollock in the 1950s. To indicate that what we should be measuring is just the vagaries of the weather and climate, but not the effects of our instruments, their exposure, and our observation times and changes around the environment of the site. In the last 10 or 15 years, various homogeneity algorithms have been developed, and they've been assessed by Victor Venema and others, and they're tested with data with known problems so we can see how well they work. But they tell you essentially what we should know, is that it's essential to know the site's history, when changes happened, and, for example, when observation times changed, and how the environment around the site has changed. But mostly this is generally unlikely to be the case. And this is not just for the oldest data, it's for the more recent data as well. So what can be done about some of these issues, which even then they might have occurred in the 19th century or earlier? And one example is a Dutch example here, is to rebuild the old screens. Some of these may be in the archives in the buildings, or they rebuilt them from diagrams, etc., in books. And so they're experimenting here with this pagoda screen, which is in the early 20th century, this screen here, which was in the late 19th century, and the modern screen is somewhere over here. So they need a number of years in order to do this. And similar comparisons like this are being undertaken in Spain. And it's also been possible to find where comparisons were made in the past, where we still got the data without perhaps realizing it, in both Austria and Australia. Now, how exposure and urbanization affect early measurements. Exposure is more early and urbanization is more recent. So the initial measurements from the 17th century were from a variety of exposures. The effect of the sun on early thermometers was well known. So a 1725 recommendation from the Royal Society by James Durin was for the thermometer to be in an unheated room. So this is pre-screens entirely. And Uppsala followed this advice from 1722 to the late 1730s. In Europe, later, thermometers were still exposed, but to the north-facing walls became the norm, until screens were developed. And Stevenson developed his screen in the mid-19th century. Glacier also developed a stand, but it needed to be moved during the day, so it was less good than the Stevenson one. And more widespread in Europe was the Montsouris or French stand, which was also similar to the Glacier one. Now, comparisons were made between these various screens in the 19th century and early 20th century, but few of these have survived. So the effects have been studied by rebuilding old screens and taking parallel measurements today, using a location where the old method is still, maybe using a location where the old method is still used. There's an example from Austria, but also work in Spain. The longest overlap of old screens and new screens, this is between the Glacier stand and the Stevenson screen, took place in Adelaide from 1887 to 1947. This has recently been written up in this paper in the International Journal of Climatology. Now, exposure issues pre-screens, and this is an example from Austria. This is from the town of Kremsmünster, and this is the Benedictine monastery there. And this is a smaller version of the unheated room, for example. So the air is exposed from the outside in this room, and the thermometers are near to that grill around the edge of the window. So there's no glass here. And the thermometers are read from the inside, and that window is in fact here. And then this is the Benedictine monastery here on the right, and some other buildings here. And this is the modern Austrian screen, which is about 2 meters in height. But 2 meters is not the standard around the world. In the UK, it's 1.2. Tends to be higher in countries which have a lot of snowfall. Now, the issue with these early north wall facing instruments is that they get sunlight during the early mornings and the late evenings during the summer, which warms up the temperatures. And so during this period, which we refer to as the early instrumental period, pre-screen, here the summers were warmer than today, but the winters tend to be close to what they would have measured. So if we're going to look at this and believe these instrumental measurements, if they're not corrected for, then we're going to get more of a seasonal difference between winter and summer, because the winters are not affected, but the summers are. And it's important to get the summers right, because the summer is the season that we know most about from natural and documentary data. Now, the other influence is urbanization influences. And this is because the instruments might have been located in a small town in the past, and that's become a big city now. And homogeneity testing may not remove all urban affected sites if all the sites are similarly affected by urban growth. And the approach here has been to assess the residual effects and by developing a data set of rural only stations. And then you can compare the rural only stations with all the stations. Now, I mention this as this might be a problem with Uppsala in recent decades. It's also important to note that we're looking at the effects on monthly and annual averages, not the effects on extreme days when certain particular weather may make the situation worse. Here's an example from London. So we have a number of series for the top panel, maximum temperature, in the middle panel, mean temperature, and in the bottom panel, minimum temperature. Now, the orange site here is St. James's Park in London, and the two green series are Rothamsted and Wisley. And you can see that over the course of the 20th century, the trend of the orange series is pretty much the same as the trend of the two rural series, northwest and southwest of London. So what this is telling us is that St. James's Park is warmer by about 1.1 degrees Celsius if London wasn't there. But because we're using anomalies from a common base period like 1961 to 90, then we could use St. James's Park because it's not affected. St. James's Park got warmer in earlier centuries before the 20th. On this slide, we're now looking at all sites around the world and just the rural sites. And this is work done by the Berkeley Earth Group in California in the early 2010s. And this shows by designating sites according to a MODIS satellite that there's no difference between all sites and rural sites. And so the urbanization influence at very large scales is negligible, but it could be important at smaller scales, particularly say for sites in cities like Uppsala. Now we're going to move to long European records. So these are series that have been developed independently. The longest are in Northern Europe, from Central England temperature, Paris to Bilt, which is Utrecht, Berlin, Uppsala, and Stockholm. And these all extend back to between 1659 and the mid-1700s. In Southern Europe, there are records from Milan, Padua, Basel, Geneva, Kremsmünster, Barcelona, Madrid, and Cadiz, San Fernando. But the focus here is going to be on the North European series. So some of the issues we're going to look at here is how well should these neighbouring long records agree? They probably should agree more when they're closer together, like Uppsala and Stockholm, for example. And how well should the seasons follow one another? So the long-term trend, say, of winter, should that be similar to the long-term trend of summer? We just don't know. And all these plots have, I'm going to show you in a minute, have the same filter. It's roughly a decadal time scale, and we're plotting the temperatures for each separate season as anomalies from the 1981 to 2010 period. There are some inconsistencies if we read about De Bilt, Paris, and Central England temperatures, and it appears that there is some interchange between them, unfortunately, so they're not totally independent. But at least De Bilt and Paris now have all their sub-daily values digitized, which is not the case for Central England. So here's Central England temperatures at the top and Paris on the bottom panel. And this starts in the late 17th century, right up to 2020. And in these plots, winter is in blue, spring is red, summer is purple, and autumn is green. And these tend to show that the trend of temperatures is similar from season to season. And occasionally you have one period like here in winters in the 1920s, which were anomalously mild in Central England temperature, but they were sort of mild in Paris too. And then there were extremely cold years, seasons in the late 17th century. The one potentially odd thing here is that the summers in Central England appear to get warmer compared to the other seasons, particularly compared to Paris, before about 1800. So this now shows Central England temperature on the top again, same diagram as before, but against De Bilt, which is Utrecht at the bottom. And again, there's more agreement in the 1920s here between Central England temperature and De Bilt in the winters. But again, the summers appear slightly too warm over Central England temperatures before about 1800. And here's the other compare here, Paris and De Bilt. And I won't talk much about this. You can look at the series and see for yourself, but they're probably in slightly better agreement with each other than with Central England temperatures. Now we move to Stockholm on the top here and Uppsala at the bottom. So again, we have winters in blue, springs are in red, summers are in purple, and autumn is green. Now we can see here that these sites are relatively close together, as you know. And they seem to agree with one another that autumns are slightly warmer than the other seasons for long periods of time. But the most alarming thing is the rise in summer temperatures at both Uppsala and Stockholm before about 1860. And they're both series are doing this. So you would think that they were consistent, but they might both have the same issue. The other feature we see here in the winter season in Uppsala is that it becomes very anomalously warm before about 1740. So we've got a sort of 30-year running average here, and in these anomaly series. So it's likely that the exposure of the instruments in the unheated room has made Uppsala anomalously warm in the first 20 years. So these are the possible issues with the long Uppsala series. The summers possibly too warm before about, say, 1860. We'll look at that later. This has been looked at in the past by Anders Moberg in a paper in 2003. It's clear that summer temperature is affected by clouds, but the cloudiness data taken at the sites had more jumps when all the observers started their estimations. It was very difficult, impossible to put a consistent cloudiness series together. Now, summer is the season of most natural proxy climates, so could tree ring reconstructions from the region be helpful? Another issue is the winters before 1740 were affected by thermometers being in the unheated room. Winters at Uppsala are strongly influenced by the North Atlantic Oscillation. So when this is positive, the winters will be mild, and when this is negative, the winters will be cold. Now, one thing we have, which we didn't have in 2003, are extended reanalyses, which go back to 1806. Now, Europe is the best place for these, as the long European station pressure data has been added. But obviously, it's only of use with the summer issue, because the warmer winters in the first 20 years are way much earlier. So reanalyses are very good because they only take in the pressure data and sea surface temperature data. And they derived everything else themselves. Now, looking at the summer temperature, this is a diagram from Anders Moberg's paper, and this is looking at the average of Stockholm and Uppsala here for June to August. And this is looking at a longer summer from April to August. And you can see that before about 1860, the summers seem warmer than they were for the period since 1860. And 1860 was roughly at the time of the sort of standardization of instrumentation with the development of SMHI. So that may have been an issue. And as a test here, he's looking as a reconstruction of harvest dates in southeastern Norway, going back to the 1750s from Øyvind Nordli. And this seems to imply that the summer temperatures should have been, from this proxy series, should have been cooler before about 1860. But whether this proxy is correct is debatable. Really, we would like to look at other proxies. Particularly, I mentioned tree rings earlier as another possibility from long tree ring series from the region of Uppsala and Stockholm. Now, looking more at winter temperatures now, I mentioned this influence between the North Atlantic Oscillation and the December, January, February temperatures. So on the y-axis, we have the NAO value, and we have a long reconstruction of the NAO back to the 17th century we're using here. And this is a plot of all the values on that in that long series from 1722 here, and against the winter temperatures on the x-axis here in terms of anomalies from the 1961 to 90 period. And you can see that there's a strong relationship between the NAO and winter temperatures. And just highlighting out the values for the first 20 years from 1722 to 1739. And although they're part of the distribution, they seem to be more towards the warmer end of the winter temperature spectrum. This is another way of plotting these values. So here we have from 1723 to 1760, we have in blue is the temperature anomalies from 1961 to 90 for each of these winters. So they're very strongly positive winters, very warm winters, very mild winters. And after about the mid-1740s, they become more variable and move to more cooler conditions or cooler temperatures. And against that, we're plotting the NAO series, which goes along with this, is that positive NAO values lead to warmer winters and negative NAO values lead to colder winters. And this is the same relationship now over a much longer period of time, from 1760 to 1890 on the top plot, and from the 1890s to the 2000s on the bottom plot here. And again, you can see the relationships between the NAO in red, and then the impacts of on winter temperatures for the December, January, February period. One interesting feature of this plot when I put it together was that the NAO was much more variable from winter to winter in the first 130 years, and the latter period there was more sequences of milder winters and cooler winters together. So more sort of not such a high frequency relationship. Now, I just wanted to end on one aspect. This is about looking at large scale temperatures on the global scale and how robust these are. And we'll be looking at annual averages here for the world. Okay, be land averages or land and marine averages. And the reason why these series are amazingly robust, and the result depends a bit on the time scale. And it depends on something called the spatial degrees of freedom. This is, although we may have 7,000 or 8,000 stations, we haven't got 7,000 or 8,000 separate spatial degrees of freedom. The individual stations are correlated with their neighbors. And so we can use this concept to look at a number of ways of how robust the temperatures are at large scales when looking at individual regions and with fewer stations and then with more dense networks since the 1900s. So we can, first of all, one of the ways we did this was to look at a network of a limited number of stations which were long. So we referred to that as frozen grids. And we determined from this, and with a bit of theory, that if all you wanted was the global average, then you could cope with about 100 well-spaced stations around the world. You couldn't just have a random 100, but they have to be well-spaced stations. If you wanted a very detailed, good gridded product, then you should use all the stations you can access. Here's some other examples of why this works. So this is a series of global land temperatures, and it's using data produced by a British steam engineer just before and just after the Second World War, and his name was Guy Stewart Callender. And he put together a series of global mean temperatures, and because he didn't have the Antarctic data, he also removed the Arctic region. So he's really looking at the period 60 south to 60 north. And we've then taken our modern data and restricted it to the 60 south to 60 north region. And we've also put on the error estimates that we think pertain to that average in terms of the error estimates related to the drop-off in the number of stations available in earlier decades. But you can see Callender's numbers, which are in his paper, in his two papers, agree very well with our modern series for the years from about 1870 to about 1950. And so his earlier work was in red here with about 500 stations, and the more recent work in 1961 used about double that amount of stations, and they're in blue, and that analysis was better than the earlier one. Now, this is an amazing result considering that Callender was using, might have had a pocket some sort of calculator in 1961, but he did everything by hand in looking at books to find these station temperature series, then averaging them together to produce these series, and did an excellent piece of work. Another example is to remove some countries of the world. And we've done this with removing the United States, the former Soviet Union, China, and Canada. But here I'm showing the most dramatic removal of a country from the Southern Hemisphere. So the top has for the globe, and the bottom is for the Southern Hemisphere. And the black line is using all the data, and the red line is using all the data apart from Australia. So in the bottom panel, the red line removes all the Australian data from the analysis. That's about half the stations. So effectively what you're getting in the red line is just stations in the rest of the Southern Hemisphere, in Southern Africa, South America, and numbers of islands around the Southern Hemisphere. And you can see that the differences from removing Australia don't really have an impact until you get back into the 19th century when the coverage is dramatically reduced. In our latest Climatic Research Unit Met Office data set, this is now for global temperatures for the land and marine regions of the world. We have an ensemble data set now to try and include more of the sort of known error components and to model that and produce series going back to 1850. And so here we have, at the top, we have the Northern Hemisphere, the Southern Hemisphere, and the globe. And the Southern Hemisphere has more greater errors because there's more regions of the Southern Hemisphere which have very little recording, like the Antarctic before the 1955 period and the Southern Oceans. But we can see that the errors of estimate are relatively small. We tend to see in both series that years which are relatively warm compared to the underlying trend are El Nino years. We have some big El Nino years in recent years, and a really big one in the late 19th century, 1877 to 78. And the years that are below the running average tend to be La Nina years. Now, 2021 is this little grey number at the end. It's only up to September so far. But 2021 is the warmest ever La Nina year. The other thing to look at as well is if you look at the Northern Hemisphere and Southern Hemisphere trends, there's no evidence of a hiatus in warming that was discussed a lot in IPCC's AR5 report in 2013. Now, the reason that calendars work uses many fewer stations and indicates that there must be a limiting set of well-spaced sites that will achieve the same as the series based on all available sites. And this is the effective number of spatial degrees of freedom. For temperature at monthly scales, this number is about 100. It will be many more if you're looking at daily time scales, and it will be slightly less if you're looking at decadal and century time scales. And it will be completely different for another variable like precipitation, which is much more spatially variable than temperature. And the fact that this number is relatively small is the reason that reconstructions prior to the instrumental series can be reconstructed from proxy data. We have relatively few proxy series. It may be a few hundred now, but they're still markedly fewer than the several thousand instrumental temperature series we have around the world. So in conclusions, in terms of station homogeneity issues, biases due to exposure and urbanization tend to be the most important components. And they're particularly important for exposure in summer because it's the summer season that we need for proxy climate calibration in Europe. Urbanization seems to be relatively unimportant at large scales, but maybe have issues at local scales. Early assessments by calendar and even earlier ones in the 19th century agree with modern land-based estimates. And the reason all this works is down to these spatial degrees of freedom. We don't need tens of thousands of stations to measure large-scale averages. We do need lots of stations, though, to get good local details in gridded products. So, thank you very much for listening, and I hope you managed to, the meeting goes ahead and you can see this recording later if you don't see it on the day.
Okay, thank you very much, Phil Jones. It was a pleasure listening to you and all the knowledge you have and you shared to us. Thank you. And as we said earlier, we are deeply sorry that you can't answer the questions. So maybe we arrange for some mail traffic for an answer for the questions. And as a gift to you, Phil, you're listening to me, I think. Hi, Phil. We're going to give you some good things, good equipments that are water related. You know, something comes down, something you, okay. So this is the thing you can do that with, I think. And this may be something you can put up like that. And also a card. We'll send all these things to you. And it stands here. Stort tack för ditt bidrag till Celsius Symposiet. Vänliga hälsningar Celsius-kommittén. That's in Swedish. I hope you can translate it. Thank you. Thank you, Phil. Now we're going to have a number of speakers, too. And we start first with Hans Bergström, colleague and friend to me many years. He's a senior researcher and an expert on the Celsius Thermometer series 300 years of weather observations in Uppsala. I'd like to say some words first to Hans. Hans has taken care of the Uppsala Times series during half a decade in Uppsala. With his great stewardship for the Time series, he both took care of instrumental failures, continued maintenance, and defended the station when it was questionized. Without Burman and Celsius, it would not have started. But without Hans, we would probably not have been able to use it as we can today. Please, Hans. And a general information. Please stand still at the microphone. And that's for all people in the afternoon. We have to stand still as cemented. So, Hans, I hope you're not cemented. But please.
Thank you. Thank you. And I must add something about the series and how it have continued for 300 years. And that's an effort of Björn Holmgren in 1958-59, when Hilding Köhler as a professor retired. And the new professor was up at Svalbard. He did a good job there. Okay, 300 years of weather observations in Uppsala. Actually, I want to talk generally about weather observations, but more about temperature observations. And especially, I want to talk about what has needed to be done in order to get this 300-year-long time series of observations. This shows the observations as such without any actual corrections, homogenizations, and it's related to long time average over the whole 300 years. And the red is then over the average and blue is below the average. Okay, how it started? Well, it started with a request or a bid from the Royal Society in London to several European countries to make weather observations to learn more about the climate variations over Europe. And in Uppsala, Erik Burman, who was, as we heard, professor of astronomy, or as I've also heard, higher mathematics, who started these observations in 1722, or as I've also read somewhere, that this journal from 1722 should have been number 9 in the series. So actually it could have started already at 1714. But these earlier observations I haven't seen at all, so we don't know if it's true. And the Celsius was, during those times with Erik Burman, an assistant to him, and he was responsible for the observations already from the beginning. And when Burman died in 1729, he took over the full responsibility, and he became a professor of astronomy himself in 1730. Unfortunately, being a professor at those times meant that you should go to other European universities to learn more. And during his absence, 1732 to 1736, there were no observations taken in Uppsala. And not during his polar circle expedition, 1736 to 37 either. So it was not until 1739 the observations occurred. But we can take care of that. We come back to that. Things needed to be taken care of before temperature data may be used. First of all, thermometer. What do we know about these old-time thermometers, which were used at least during the first 30 years? Their scales, their calibrations, which were sometimes absent almost or very poor. I can mention that one thermometer was the Hawksby thermometer, which was used for many years in Uppsala, and there were 3 of those Hawksby thermometers in Uppsala, and they made comparisons during the 1740s and found that they could differ with as much as 12 degrees between each other. So they are very poor in construction and or calibration, I don't know. Then we have thermometer locations. Where did we put the thermometers? In a screen or whatever. Then we have the observation times. In order to get the average temperature, we should have some knowledge about how these observational times were related to the daily averages. We have to deal with periods with missing data, as when Celsius was absent. And finally, but not least, the urban heat island effect, as Uppsala has been growing. First, let us look at the thermometers. This is a list of all thermometers I've used, which they were measuring with in Uppsala. And we can recognize some of them, Celsius and Celsius Original. Fahrenheit, de Lille, we have heard something about. I think he was a very good instrument thermometer maker. And I heard that he used his primary calibrations down in the deep cellars below the Paris Observatory, because there the temperature was constant, so you could get one fixed point in his thermometers. We have a Hawksby Klingenstierna, Hawksby Berman, which we know about. Then we have some thermometers which I don't know much about. But we can make regressions between the different thermometers. As to the right, we have Celsius Original with 100 degrees as freezing point, and the modern day Celsius, which I think Ekström in Stockholm made the first scale of. They agree very well. We have the de Lille and the Celsius Original to the left, and so on. And going back to this graph with the old thermometers, we can see that they knew about this problem with the calibrations, so they made contemporary observations with several thermometers. We have Celsius and Celsius Original here. We have Celsius and Fahrenheit, Celsius and de Lille, Celsius and Hawksby, and so on backwards. So we can really go by simple statistical analysis and regressions back in time and recalibrate these old thermometers, which we don't know the accuracy of. So that's kind of fixed now. Then we have the thermometer locations. And we heard Phil talk about the James Durin recommendations from the Royal Society of how to place the thermometers to make accurate measurements. And James Durin said, I read somewhere, a well-ventilated north-facing fireless room. That doesn't tell us very much. It tells us that they knew that you shouldn't have any sun shine on the thermometer, that it should have some air flowing around the thermometer, but not any details. And we will come back to that. These kind of observations seems to have been used up until 1739, and as a consequence, the thermometers are then likely to be too slowly varying and not having a good representation in the measurements of the daily variation. Okay, if we look at the daily variation, this shows for the 12 months of the year. In the full line is the monthly averages between 1961 and 1990. And the crosses show the observations 1722 to 32. And we can see, especially during spring, summer, and early autumn, that we have too low temperatures in midday and too high temperatures in the morning and in the evening, if we take 3 measurements a day. And of course, this can be corrected for, and I've done that with one correction algorithm and get this ring markers instead. But what is luckily is that making averages from the original data, not corrected, and comparing with the corrected data, they differ very little, just 0.1 to 0.2 degrees. So this is actually not a big problem if we are looking at the average temperatures. Of course, we don't know if this poorly ventilated north-facing fireless room could give us any systematic errors. And luckily, they made observations also of the precipitation. And I've compared temperature with precipitation type, if it's rain or if it's snow. And we can make a graph of this, and we have temperature here on the x-axis and the percentage of liquid precipitation on the y-axis. And 1962 to 82, we have the crosses here, which goes rather steeply up, crosses the 50% level at about 1 degree Celsius. 1739 to 50, about the same, but 1722 to 32, we see that they lose much of the variation which we should expect, and too much liquid precipitation at low temperatures, and too little liquid precipitation at low temperatures, and too much, and too little at too much snow at high temperatures. But we can conclude from this that we haven't any systematic errors around 0 degrees. So in wintertime at least, the old time temperatures should be quite accurate, in spite of the poor location of the thermometer. Yes. From 1739 and onwards, we have notes, not very much, but notes telling us that the thermometer is located outdoors in the free air and in the shadow. There are some notes about the thermometer outside the window and the thermometer on a shelter or screen of some kind, not described at all, on the fence to a neighboring garden. Mrs. Dahlman's fence. But similar daily observations have found for this data since 1739 as for present days. So we leave the thermometer locations. Of course, much more could be said about that, about different screens and so on coming into use on the 19th century and so on, but I leave it for now. Observational times. During the old days, these times were varying very much. So it could be from just 1 to 3, 4, even 5 observations per day. But typically, we can see from this graph, 1722 to 39, we have 2 or 3 observations per day in the peak. 1, 2, 3 in the 1739 to 50. The same 1751 to 99, and from 1800 to 1831, almost always 2 observations per day. From 1832, they have fixed hours, 7, 14, and 21 hours, 8, 14, and 21 hours, 1863 to 65. And since June 1865, we do have hourly observations from Uppsala. But what to do with this early data? Well, as it turns out, they knew something about the daily variation of temperature. They knew that at sunrise, the temperature was commonly at its minimum. So they took observations in the winter at about 8 or 9 o'clock, and in the summer about 2, 3 o'clock. So they followed the minimum of the temperature during the morning observation, and the afternoon observations was about 2, 3 in the afternoon, where we have the maximum temperature. So we could simply just calculate the average of this maximum and minimum, but they are approximate, and I wanted to do something a bit better. Of course, also as we don't have these 2 observations always, we sometimes have just 1 observation or maybe have 4 observations. So again, I compared with more modern data. The hourly observations 1869 to 1958. And these graphs show for each month the deviation, the difference between the daily average and the hourly averages during the whole day, the 24 hours. And we could then calculate the daily average as the sum of the individual observations, 1, 2, or n observations, plus this difference between the climatological daily average during each observational hour and divide by the number of hours. In that way, we are not dependent upon how many observations they made and the exact hours they made the observations on. The missing data. Well, 1732 to 38 is the longest period with missing data. And we have here markers showing where we have data, where we don't have data, the gaps. So for Uppsala, we have 95.3% of the time since 1722 covered with data. And the major part of data during the 1732 to 38 was covered by station Risinge in Östergötland, down here. So we have used some stations in eastern part of Sweden here to interpolate when we don't have any data. So only 0.1% of the time we didn't find any data to interpolate to, and we have used Stockholm, Linköping, Bettna, and Risinge to get the full Uppsala series, and then again used regression analysis to get as accurate data representing Uppsala as possible. Of course, this isn't true for each individual day, but it's probably quite correct for monthly averages. Urban heat island then. Well, as we know, Uppsala has been growing over the centuries and decades. And to start with, I made, together with Anders Boberg, the standard normal homogeneity test for Uppsala as he did for Stockholm. It's a test which Hans Alexandersson developed in the 1980s. And it's been used quite a lot for stations in Sweden. There we compare each stations to a number of stations in the region which should have the same general variability in the temperature. And in doing that, we end up with the annual variability caused to urban heat island effects and other effects according to this curve here. And we see that there are jumps in the series, and these jumps can almost always, or I should say always, be identified as something happening. We know that we moved from the old observatory, the Celsius house in the center of Uppsala in 1853. Then we came out to what was then outside Uppsala, the new observatory. This was an urban area in those days. Then Uppsala started to grow. In about 1950-51, they moved the observational site to a small hill a couple of 100 meters from the observatory. It was more open and not the parkland, so it's lowered the temperature. Then we moved back to the observatory park, and then they started to build new blocks of housing about 0.5 to 1 kilometers from the observational site. We moved to where we are nowadays, Geocenter, which was then more suburban than it is today. And then they started to build huge blocks of new buildings in this area. And we get what we find today as an annual average temperature, which is about 0.6 degrees too high as compared to if we didn't have Uppsala here. When using these urban corrections, we can see from this graph that we can't just use one annual average. We must use monthly averages because it varies, the magnitude of the urban heat island varies over the year. We can see that it's highest in the spring and summer and lower in winter and autumn. This orange curve here is the present day monthly urban heat island correction. It's interesting to see this maximum in March, and then a lower value in April, and then a higher value during summer. And I can't really explain it, but it's the same kind of variability is seen in Stockholm. So it's really something which I believe is true for some reason. Okay, so we end up with the annual mean temperature variations observed and 30-year mean. The dots are the actual observations, and the dashed line is the observed 30-year mean, and the red line is the homogenized urban heat island and otherwise corrected 30-year average. And we can see that we have the difference of about half a degree or so, or 0.6 degree nowadays. I could mention that this correction in the early years is based on comparisons between Uppsala and Stockholm, and of course it's not as correct, but it's not that large, 0.1 to 2 degrees or so. But it seems that the small city of Uppsala during those days were causing an urban heat island, although not as large. Then we have this warm years, 1720s, 1730s, which we of course could doubt the accuracy of. And Phil showed this in a graph, and we saw some similar things in other of the stations, Central England, the Bilt and so on. But anyhow, I doubted this accuracy for the reason of the poor location of the thermometer in a ventilated, unfired room. But then I happened to talk to oceanographers at Göteborg University, Anders Omstedt and Daniel Hansson, who made analysis of 500 years of sea ice in harbors around the Baltic Sea. And they made some sophisticated statistical analysis of this using modern day data, and reconstructed from those ice observations a 500-year-old wintertime average temperature, annual average temperature. And we can see this in the bars and the thick line here, which is about 10-year averages. And we can see here a warm period. And if we compare with the Uppsala series here, we can see that it coincides with the maximum we have in Uppsala, 1720 to 30 year decades. So I believe from this purely independent harbor ice observations that these early data are really correct. It was a warm period, almost as warm as the present day period. It wasn't long, but it was for a couple of decades. And I think it's fascinating to see that if we follow this two temperature series, the blue line, the 10-year average here, we can see this maximum here. We can see the period during the mid-1800s with smaller variations. We can see the ups and downs coming into the 1900s and so on. So it's fascinating that they could reconstruct the temperature with this accuracy in the 10-year averages. And well, finally, I think I have time to say something about this graph, and it relates to the question, a more extreme climate or not. We always hear that the climate is more extreme nowadays. And it may be so, but it may also be an interpretation of what we mean by extreme. I mean, if we have a distribution of temperatures and increase the temperature average, then of course we will get much more high extreme temperatures, much more temperatures above 30, 35 degrees. But is it really more extreme? Or is it just that we move the distribution towards a higher average? Or we could really have a true increase in the extreme, meaning that the distribution will widen at the same time perhaps that it gets warmer. Then it's really getting more extreme. So this graph shows the standard deviation, the annual standard deviation of the temperatures series of the 300 years in Uppsala. And we can see that the standard deviation seems to have gone down. So it's less extreme nowadays than it was in the 1700s, for some reason. I just thought that maybe it has to do with if it gets warmer, we warm up the Arctic area more than the more southern latitudes. This might have the influence that we don't get that huge cold air outbreaks in the winter time, and this would make the standard deviation smaller. Could be. I don't know. I just looked at this graph for the last week, so I haven't seen it before and I haven't done it so much thought, but I thought it was interesting to see that it's not all data which tells us the story that the climate is really getting more extreme if we look at the annual average temperature and its standard deviation. So I think I end there with this graph showing the homogenized urban heat island corrected Uppsala series with a cold period in the 1800s, maybe a bit warmer in the 1700s, and definitely much warmer in the present half decade or so. Yeah, thank you.
Thank you. Well, I would like to start with one question to you, Hans. I've seen you working with this during all these years, and I would like to ask you, what was the most interesting part of your work with the series? You were down at Carolina, you were down in the cellar looking for things, you are on many positions. What was the most interesting that you said, aha, eureka, or something like that?
It is, I mean, I'm kind of a collector. Yes. So I collect stamps, and this collection of early time data to get the complete series, that was my aim and my goal from the beginning. And then we always have notes in these old journals about the Northern Lights, about what do you call it, kulblixt.
Ballblixt, man.
Ball thunder.
Ball thunder.
I don't know. There are many.
Ball lightning.
Yeah, and they always they also had notes about sound propagation.
Oh, thank you.
Might interest you. They notes when we heard the bell of the Vaksala church, and they connected that somehow to weather, to wind, and so on. So there are very many interesting things in doing this. It's of course just boring printing numbers on the computer, but when you do it, you get 1 month more, one average more, and then one note more. So it's really this thing making it complete, which is interesting.
Fine, very fine. And now, questions from the auditorium.
Yes, I have a question, but not to Hans, but rather to the university and faculty leadership. Because as you started, you said that more or less by chance, people have upheld this series, and there has been no official order or mission or anything, although the university is honoring this thing and creating symposia and honoring Celsius' name. I have not seen anywhere any official written order or mission saying that this should be the duty of the department to carry on into the future. So we keep on the 300-year series for another 50 or 100 years, and it won't be dropped because nobody really cares.
Okay, the question.
Yeah.
the question was, how could we secure that we have 300 years or more of this going on? We need money from the university. We need money from the state. Or what do you say?
Well, it's really not my task to say, but I can just agree. We have, by luck, made the series survive several times. I mean, we can go back to 1760s, 1730s, 70s for the first time, and then there were 1830s, and then we go on, and it became interesting again with the hourly observations and the Thermometer machine, the thermograph. Yeah, it's up to you being in head of the department and the university to keep this secured.
Yes,
I agree.
Because it's very important. I told you that you also defended the station when it was questionized. And I remember while I was coming on the bus, and then I had to go a little bit to the work. It was some years ago, and we had moved. And I saw two people working. They were highly up in the building, in the university building department, and they said something about we have to move this, and pointed to the station. I looked at them and introduced them to who I was, and then I was so crazy. So I in my full speech, I said Celsius had turned around in his grave. And after I said that, I backed and said, "What was I saying?" And I said, "Wait a minute, I send down Hans Bergström," and I think you were down there and explained it more with more words that could be
calm.
Yeah, more calm situation. Then I was furious. Okay, thank you for your presentation. I'm gonna give you something. I think you can need it.
A long thing.
A long thing and a short thing and a nice card. Thank you. Thank you, Hans. Okay, now we have to move to Anna Rutgersson. It's going to be there, steady as cemented. Anna Rutgersson, you know her. She's introduced it this day. She is a professor of metrology, and she's going to talk about current technology and observations for future forecasts. And I have to tell you a little bit. Anna's work also relates to measurements, but using more recent observational techniques compared to the under Celsius that we have seen. Anna's research is focused on air-sea or air-lake interaction, and the processes influencing atmospheric turbulence, air-water exchange, and of momentum, heat, humidity, and greenhouse gases. Okay. We fixed the batteries in the microphone. Okay, Anna, please.
Thank you, Conny. Nice to stand here again. We have spent the earlier part of this day looking mainly back and heard very interesting presentations. I will try to link this and look a little bit forward. What does this very nice work that has been done for the past 300 years, how can we translate it to today, and what should we do in the future when it comes to observations? So we have planned this celebration for quite some time because we knew, of course, it was coming up. So I've spent some time in thinking about this with observations. So one of the questions that I've been dwelling on is why do we need metrological observations? As I tried to think about that myself. And then I started with trying to imagine what other people would think if I asked them this question. So I thought that if I asked under Celsius, he probably would say, oh, I want to understand the atmosphere. if I would have asked Hugo Hildebrandsson, he was the first professor of metrology in Uppsala, and he did a lot of work in creating common ways to describe the clouds. So he probably would have said to characterize the variations in time and space. And then I thought, what would a climate modeler think? So then I was using Erik Hellström at SMHI, who does climate modeling. What would he think? So then I thought maybe he says that we don't need observations, we have models instead. So. But then going to the IPCC, we need to validate the forecast or the scenarios of the future. So he would probably have said that climate models need to be validated. So we have meteorological observations for climate, but we also have them for weather. So then I thought, what do we do for weather? And Helene Andersson, who I think is here, head of research at SMHI, she probably would say, oh, we have promised the Swedish government that we will make better forecasts, so that's why we need the observations. And I thought, what I'm myself supposed to think? I want to develop a better world. That's probably what I'm supposed to think. But then I realized probably to be more scientific about this and ask people instead of imagining up what they would say. So I almost asked Anders Celsius. I asked so close that I could, so I asked Martin. And he said that he probably did these observations just by curiosity. I asked Erik, and of course he thinks that we need observations. So he said that, we need observations for development and validation of the models. And I asked Helene, and she said, observations form the basis for understanding of our environment. So very clever comments. I didn't manage to find anyone to ask about Hugo Hildebrandsson or the chair of the IPCC. So we'll have to think that they thought this. And if I ask myself then, why do I make observations? And I must admit, I do it just for selfish reasons, because it is so fun to be out in the field and working. But then a little bit how we use the data. So I tried to look back. So what data what is important in the data that we use? And the longest running temperature record started 1659 something. We have the Uppsala record that we are celebrating today, 1722. When the data was so dense enough so we can make these databases that we heard Phil talk about this morning, it was approximately 1850. So then we could make global estimates of the global temperature. 1880 was when Hildebrandsson started to do this more international standardizing clouds and also observations. Then came new types of data that has been really revolutionizing for the metrology and the climate research. We have radio sounds to get profiles of what is happening in the atmosphere. The satellite has made a huge difference, because then we have a spatial distribution of the properties of the atmosphere, which is really important. And the HAD crew data that we heard about before is the gridded global data using all existing measurements came 1986, something like that, which has really been a valuable tool for people working with climate and climate change in the past. Then mixing data and models gives us the reanalysis products, and they came a little bit later, and those are frequently used nowadays to understand and describe weather and climate. Parallel to this has been development in numerical weather observations and climate models, which is the tools that is used. So how do the observations come into this, and how do we mix the understanding from data to modeling? And then back to the question, why do we need observations when we have numerical models? Of course, we need data to feed into the models. And then from the way I see it, there are two different ways of doing it. For weather forecast is mainly an initial state problem. We need to have the initial state described as good as possible, and then we need the data to give us this state, and then the model can run by themselves. Climate is a little bit different. We want to describe and look at the changes of climate, and it's more a forcing problem. We want to understand the forcing and the changes in the forcing in order to describe climate and climate change. And for this, of course, we need data. So for the models, also for the development of the models, we need data for the process understanding of the models. And for the data assimilation, the initial value problem within the data, but also for the validation. And this goes both for weather and climate models. So now I talk about data and models. And of course, then we have these different data sources when it comes to gridded data or reanalysis data. So, linking a little bit more into the weather forecast. I start with the weather forecast and then I will talk a little bit about the climate. So, weather forecast, we have a forecast model. I'm supposed to have a pointer here. So this is an illustration of a weather forecast model. We have a grid in horizontal resolution and in vertical resolution, and then we calculate for each time step of the model. We calculate the properties and the development of the atmosphere. And this is where the data assimilation comes in. So here is our model, an illustration of that, and the illustration of the observations. So we have surface data, we have balloon data, we have aircraft data and satellite data. And in the data assimilation, we tune the atmospheric state into the observations. So these are different ways to do this. But in order to get a good weather forecast, we need this tuning between the observations and the model state. And then we can run the model for our forecast period. And then this procedure is very dependent on the data that we have. So the forecast error depends on the data that we have for the data assimilation, how good the initial state is. So this lower figure here illustrates the type of data we have for the data assimilation, and this other figure is from Adrian Simmons from the ECMWF. I got it from Linus. And for the figure, we have two different colors here, which represent a 3-day forecast, a 5-day forecast, and a 7-day forecast. And there is a band, an upper band and a lower band, and the upper one is for the northern hemisphere, and the lower band is for the southern hemisphere. And then we can see that for the forecast, for the early part of this period, is a big difference between the forecast skills when it comes to between northern and southern hemisphere. And this is, of course, is due to the fact that for these time periods we have very sparse data coverage from the southern hemisphere. So the weather forecast skill is much less good in the southern hemisphere. When there is higher frequency of buoy data and also introduction of better satellite data, the difference between the northern and the southern hemisphere is much less. We can also see that the skill has increased over time due to better implementation of more data and better data sources. So the data is really a key, and the right type of data is really a key for good weather forecasts. Then what type of data we need is something to think about. And I have one example here that I find quite interesting. Nowadays we think COVID influences everything, and the question then stated here is, did COVID influence the weather forecast? And actually it did. So this is an example of what removing almost entirely one type of data source can do to the error forecast. So up here you see before COVID the number of aircrafts over Europe, and then during COVID there was a strong reduction of the aircraft. And of course the airplanes take measurements and they send them into the assimilation systems. So when we remove these airplanes there is less data from the aircrafts. And then at the ECMWF, they did a simulation, so with aircraft data and without aircraft data. And here is the bias, the difference between the simulations with and without aircraft. And there is a difference, and it's less accurate. So this is for a 12-hour forecast, a 72, and a 120-hour forecast. So there is a reduction of the accuracy of the forecast if we remove the aircraft data. This main impact is here on the upper air, wind and temperature, and this is for the northern hemisphere. But of course this error also penetrates slightly down to the surface. So some examples of what the data means for weather forecasts. And then I will go to some examples what the observations means for climate, understanding the climate. And this has been touched upon by Phil, and this is actually a figure from him, where we have the global mean temperature and use the gridded data products. So there are several gridded data products. So the head crew is from Phil Jones' group. And then there are also other data sources, NOAA and others here. And we can see that there are some differences, in particularly early on in this period. And it is due to the fact then that there's different data sources and different treatment of the data. And one particularly interesting thing here, I think, is the yellow, the comparison between the yellow and the red curve. And this is having correct sea surface temperature observations. It makes a big difference when it comes to the climate, the accuracy of the global mean global mean temperature. But the gridded data products is a key to understand past and present climate change. And what we can learn from this gridded data is that we have over 1 degree warming compared to pre-industrial levels. Looking a little bit more into these gridded data products, this is also from Phil. And here is the number of data in different latitude bands. So going from the 90 degrees south to 90 degrees north. And here is from, from 1890 to almost present day. And we can see that there is a difference in the data coverage between the northern hemisphere and the southern hemisphere. So also for the climate model, of course, there is a huge difference in the quality of the product. The SST data is a key also to, as I said before, the SST data, the sea surface temperature data, is a key to get the correct description of the climate change. The question that is very relevant today is not only what climate change we have experienced, but we are also interested to know what will happen in the future. So how can we use the observations to get better climate scenarios and better climate knowledge for the future? So a climate model is similar to a weather forecast model, but we don't have the data assimilation, but we need to have a correct forcing. And we use climate model to simulate the future changes. And the forcing of a climate model is, of course, the sun that forces everything. If we have changes in the solar radiation, it will influence the climate. But the main forcing that we know is changing is the amount of greenhouse gases and aerosol. So one major uncertainty, of course, when we look at the future climates is the amount of greenhouse gases and aerosols. So this is where we have scenarios. We need to make some assumptions of the radiative forcing. And this is from the last IPCC report, where we see the global surface temperature change relative to a reference period. And we have then these defined 5 scenarios for the future. So the forecast for climate is that we will have a warming, which then depends on how much greenhouse gases we will emit. So we all know that we aim for 1.5 degree warming. It is lower here, but the upper one is where we are heading at the moment, it seems, from the emissions and the changes of the emissions that we managed to do. So these change mean a warming, but we also expect from the climate models a reduction of the Arctic sea ice area, then depending on what type of scenario we have, and other parameters also are expected to change. Here is the global mean sea level change relative to 1900, where we have these different scenarios. So where do the observations come into here? We have the climate models, we can have them to describe the future climate. So do we really need observations to get predictions of a changing climate? So the climate models of today are good for global mean temperature, good for mean states, and larger scale processes. They are less accurate when we go into the details. Looking at small scale processes, regional changes, there are still some lacking information from the climate models. So what we do need when it comes to observations to get better predictions of a changing climate is better description of the processes in the models. And we also need more data for long-term validations of the climate models. So global mean temperature is one example of something that is probably quite good. Here is also from the IPCC, the observed change from, and then the modeled change. And here's a difference whether we take into account the human impact or not from the climate model. So we see very clearly that this warming, the models can reproduce the observations when we take into account the anthropogenic effect. So here the models do a good job. But when we look, for example, at the precipitation, this is one of the global models, the Easy Earth global model, and looking at the precipitation, the wintertime precipitation, and the difference compared to measurement. And we see that there are some biases, there are some difference when it comes to the precipitation, and it's different for different regions. So, as I said, when we go into other parameters than temperature and we go into regional differences, there are still problems with the climate model, and we need to have development of climate models. And one example then on one example of uncertainties, one other example of how we can make the climate models better is data also again from Erik and his group, where they looked at the heavy precipitation in Sweden, and it turns out that convective heavy precipitation results is strongly model resolution dependent. So going from a horizontal resolution of the grid from 12 kilometers to 3 kilometers gave much more intense precipitation from the model. So here is intensity and precipitation in millimeters per hour. So the higher resolution simulation, the red curves here, well reproduces the observations. The lower resolution underestimates the most extreme precipitation. So it means that going into the details, the extremes, we need to have better models. And having these higher resolution models, we also need to understand the physics on these higher scales. So that puts large constraints on the observations. We need observations in order to have describe the processes correctly on this higher resolution scale. So I strongly think that we cannot continue developing our understanding of a changing climate unless we continue to have good quality and improved observational systems. That brings me to the work that we do in my group and I do. As an example, of course. So one example is to use data from our Östergarnsholm site in the Baltic Sea. We think there that we need these observations to understand processes. And the processes that we are looking at, I use here as an example, it is the air-sea interaction. How do the atmosphere and the ocean interact? And how can we then use observations to describe this? So we have turbulence measurements, and that means continuous measurements with a frequency of 20 hertz. So we measure 20 times every second. And that gives 17 million data points per day if we look at all our system. So this feels very nice in comparison to what we heard about under Celsius, where they had 2 observations per day. So 17 million is a little bit more. So what processes we are looking at then is so how do these air-sea interaction influence the mixing, the vertical gradients in the atmosphere and in the ocean carbon uptake and emissions, surface friction and heat fluxes. So this is what we want to improve in the climate model, and we think that if we improve the description of these processes in the climate model, we can get better climate forecast and better climate predictions. So one example of what we are looking at here is how do surface gravity waves influence the atmosphere and the ocean, and then we have realized that there is a number of processes that are being influenced by the surface waves. So then we construct better descriptions, better process descriptions. We implement it in this case, a regional climate model, and then we can look at the difference. So for us, what the result was when we introduced this, is that we got an improved or a changed surface winds. So it was different changes differently for different regions, but sometimes an increase and sometimes a decrease. But we get an improvement in the wind description when we include more processes. So linking this to the climate models. So I think that we need observations, we need to understand what the observations tells us, and we need to implement this new knowledge into climate models. And from my perspective, the major processes in the climate model that needs development, where we really need good data, is aerosol and cloud interaction, which is a difficult problem in climate models, the ocean response to a warming, then we need to improve the ocean processes, and also carbon cycle feedbacks. So this is my perspective. I guess there are others who thinks otherwise, but this is how I see it. So trying to link this for the future, what types of observations do we need in order to get this better understanding? And there is an ongoing development. So there's a development of observational platforms. We have these unmanned vehicles, drones, so we can get more detailed understanding with high resolution in horizontally and vertically. So this we can get by drones. There are this more imaginative or platform. There are this deep diving seals with instruments on them that go and dive under the Antarctic ice to get information of the properties of the ocean under the ice, where it's not possible to get any other. Of course, further development of the satellite products. In remote sensing also, ground-based remote sensing is something I think really can push the knowledge forward. Also trying to imagine some new things. Can we use signals from phones or from cars to get a more dense network of observation? Is this something that we can use for the future? There is also an ongoing development of sensors. They are lighter, they are higher quality, and this of course then also can improve our weather forecast as well as our climate description. I think what is also important here is development of analysis method and statistical tools. So different statistical tools can teach us a lot, machine learning, artificial intelligence, and also enhanced computer resources is of course then the basis in order to do all of this increase in data and methods that I think is necessary. So if we think ahead, observations for the future, where are we? Today we are celebrating what has happened for the past 300 years from Celsius Day to today. So if we try to look 300 years into the future, what will be the observational systems that we have then? So I've been thinking about this all summer and I couldn't come up with an answer actually. So then I'm thinking we have a lot of nice, gifted, talented PhD students and students here. So that they are illustrated by some of the students in my group. So I must turn to them, and I hope that they are the ones who can figure out what is the way for the future when it comes to observations. Thank you.
Okay, thank you very much, Anna. And as Anna said, okay, solutions of this question. We have a lot of very talented people. Please, Martin.
Short comment. I noted you showed the possibility of using seals as a modern tool. That was the tool of Celsius in 1731.
Okay.
That's true.
Yeah.
Okay, so the seals are the old-fashioned ones.
Yeah.
We use
Seals
them in a different way.
Yeah. It was a comment from Martin here that also Celsius used seals. So any suggestions, solutions? What will happen after in the coming 300 years?
Fiber optics network.
Fiber optics.
To measure temperature.
Okay, fiber optics to measure temperature. Okay, I think you can think about this because the time is now 4 o'clock. And thank you, Anna. And the presents I will leave to after the panel to you, because otherwise you have to carry them around here. So it's time for the next thing, the open discussions between invited researchers and experts. So if you take that microphone and then carry it over to here, oh, you're going to fix it. And then I go around here, and I will position me here, I think, close to the flowers here. And then I ask that Linus, Gunilla, and Anna is already there, and Eric come up to these two tables here. Okay, and I'll start with Linus, standing there. Linus Magnuson is a senior scientist at the European Centre for Medium-Range Weather Forecast. And you're working as the forecast department, evaluation, section, diagnostics. Oh, that was very long. And I would like to say that Linus represents the weather forecasters, predicting the weather today, tomorrow, and the next week. Something like that. So I would like you to say something more about yourself, what you're working with and so on, and then answer my questions. What are the observational needs for improved weather forecasts? Please take the microphone over there. No, please.
Thank you for the invitation. So my everyday work is to understand the errors in the forecast and try to find their origin and hopefully make a step further to the solution and improving the forecast. And as Anna pointed out in her talk, one can divide the observations into three kinds. We have the bulk of observations that goes into our data simulation to improve the initial condition of the forecast today. Then we have the observations that we use for verification of the forecasts. And then we have the detailed observations to understand or improve the processes in the forecast. And these three different kinds are a little bit overlapping, but one can see them as different groups and different demands on the quality. And it might be the opposite of what you think, but the part where we need, in one way, the lowest quality, where we care less about the level of quality, is what we use in the data simulation. The important thing, what goes into the initial condition, is to have a good knowledge about the quality and the biases, because then we can specify it and have a stable system in our data simulation. While on the other hand, for the detailed observations that goes into process understanding, like the Östergård-Holm, then we really need a good standard on the quality, because, so we are not hunting down observation errors when we try to understand model errors. So thinking about the requirements, availability, we need to easily gain access to observations, because for myself, working with observations around the world, I cannot try to hunt down every single station in the world myself, because that I'm not having time. So having a system to get the observations pushed to us or sent to us. Then thinking about the future, we heard from Anna, we have all these short new development, but the advances in technology is going so fast. So thinking about the Celsius, we have had the same kind of thermometers or instrument for 300 years. Now when we're sending up new satellites, there are instruments that only live for 1-2 years. And then it's for us to think about the trade-off. Is it worth investigating the time to get these observations into the system before they disappear? Because as I said in the beginning, what we really need is a good knowledge about the error characteristics to use them in our forecasts. And the final point is that was also touched upon is the resilience in the system. We get around 500 million observation into the house every day. And of course, if one take out 1 or 2 observations, it's very difficult to measure the impact on the forecast. But what's really critical is the resilience. So when, for example, the aircraft observations disappear, that we have other system that step up and fill in that gap.
Okay, thank you. And the next person in the panel is Erik Källström. You're a professor in climatology at SMHI in Norrköping. Your work is within a Rossby Center as a part of a research department at SMHI. Erik is working with regional climate models, you can say. Please, I have a question which I've stolen from Anna, I think. What is the observation and needs and challenges for climate research and improve climate projections? Or to be a little bit more provocative, do you really need observations when the climate models are so good?
Yes, indeed. Thank you, first of all, for inviting me and all of that. I think the climate models, they're of course good, but of course we need observations. And thanks, Anna, also for saying that before. There is no doubt about that. I will just start quickly with the long-term historical perspective a little bit first. I think that's more important, and then I will get back to the models in a while. I think this is a very nice experience today here to be here celebrating this very long time series, the Uppsala series. And when we now get to the weather forecast models and also the climate models and today's climate problem and talking about the future, this long-term perspective is something we really need to keep in mind and think about. So of course these observations are important, first of all, for the monitoring part, I would say, so we can follow what's happening. What is the climate change signal we are observing, and what is variability, and what are the changes? So that's one very important part, first of all. And then you immediately start to think about the question of trying to attribute changes to potentially to greenhouse gas changes and to human-made force changes in other types of forcing, like aerosols or land use, etc. So it's very important also to have the observations there to be able to understand these things. And this leads me a little bit into also the Uppsala series and the things that Hans was showing. You talked about the urbanization and the modifications, homogenization process you have gone through to try to use these data in a more comparable way over the long-term time series. And I think these are really interesting things, and I think there are still scientific things to work around there as well. Also looking not just at the urban area itself, but also what's happening around in the landscape. In Sweden, there have been tremendous changes in the landscape over the last century in terms of reforestation. We had an earlier deforestation in hundreds of years before of that. And there has also been a very strong change in the number of wetlands in Sweden. And that would certainly have an impact on regional climate features, I think, and also in the temperature climate, but that is not so investigated so far. So I think that's an interesting thing to look into in the future as well, with the observations, but also with the models. And now I will come to the models, since this is what I'm working on. And the evaluation, of course, of the models to try to see that they are working in a as good way as possible. That's really important. And as a contrast to Linus and the weather forecast models, we don't have the data assimilation possibility here really. So we'll need to really rely on the long-term data series with observations. So I think that's to have long-term homogenized data, preferably gridded, that we can compare them with our models. And as Anna was saying, we are looking at these very high resolution models now at only the kilometer scale. So that also, of course, requires very, very good observations at the high resolution. We can, of course, try to implement and use also satellite and remote sensing data to improve the resolution. But again, we get back then to the problems of homogeneity over time, since these time series are fairly short. And then we need the long references also to tie everything together to stations like Uppsala, for instance, etc. So I think that's very important. So that's for the models, and then of course also to try to understand things like extremes and things that have impacts also. So it's not just understanding the climate system, modeling it, and simulating things, but also to try to describe weather phenomena and what kind of impacts certain extreme events can have is of course a major thing, and something we are working a lot with at SMHI. We are there to provide climate change information for the society, for climate change adaptation, etc. And there again, observations are important, since even if we are working with our models for 10 or 100 years from now, there will still be biases in these models at the very end for certain. And that means that making certain impact studies will be very difficult. So we always have to look at these biases, and sometimes we are doing things like we talk about bias correction or bias adjustment. So we are changing our results a little bit in order to be able to run hydrological impact models on the results, and that's one thing we need to do as well. So yeah, I will stop there, but I think these are things that we are working on.
Okay, thank you, Eric. Then I turn to Gunilla Svensson, Professor of Metrology at Stockholm University. Gunilla has been working with global climate models and how to describe small-scale processes as turbulence and clouds in the models. I think a focus area is the Arctic area, maybe with the stratus clouds there. So you can introduce yourself more, but a question from me is, what new methodologies and techniques do you see in observational systems? Please, Gunilla.
Thank you very much, and thank you for the invitation to come here and talk. And I really enjoyed the talks of today, and to reflect on this question of what observations mean to us. And when I started thinking about what to say, I was doing exactly the same as Linus said. We have different kinds of data and different kinds of meanings of the data, and we need to have a balance between these three. And being a university professor, I'm mainly curiosity-driven. I want to understand how the atmosphere works. And to do that, I use observations in combination with models. And when I talk about models, I talk about detailed process models to understand the processes that we're interested in. And as Connie just mentioned, clouds are one of them, especially mixed phase clouds, which are clouds that contain both ice and water. So, then the temperature becomes very important for when you have one or the other. It's really important for the climate and the climate signal, and important for the Arctic. It's also mixing, and especially in stably stratified conditions, which you have for a long time of the year in our part of the world, and even more when we go to the Arctic. So my research is curiosity-driven, and I want to understand how well are these processes then described in the weather forecast models and climate models. And I think that we have very good models. They perform very well. We have good forecasts, but these models contain a lot of compensating errors, I must say. And using process observations, we can find out when and where and why they are. And when I talk about process observations, I talk about things like the one that you showed on Östergarnsholm, because weather forecast models, as climate models, are coupled to the ocean. And ocean is a really big part of this. And we need to understand what's going on there in the interactions there. And that becomes even more problematic and interesting when we go to the Arctic and Antarctica, where we have sea ice and we have ice on land. And that's a really complicated problem. What does our models do there? And so that's one thing that I'm interested in. And there was just recently a study published about Arctic amplification. You probably all heard about that the climate change goes much faster in the Arctic regions. And we used to say that it's twice as fast as the global. Now there was a study that looked at the last 43 years. I think it was the 43 years. And it's up to 4, maybe even 6 times as fast. And that study also compared what our climate models are showing as this Arctic amplification. And none of the climate models were able to do such a rapid change. So there's something going on in the Arctic that is not captured at all in our models. And this is a problem, of course, if you want to understand, especially we live far north and we have a lot of climate change here, and even more influenced by the Arctic. So last week I was in Canada. We had a final meeting for our 10-year program on polar prediction. That is a project that has been organized and driven by the World Metrological Organization. And we talked a lot about, for these 10 years, and how to improve the predictability of the polar regions. And we've started, and we've come a little bit, but we need to work further on this. There's a lot more to do, especially when it comes to detailed observations about this couple system. And there has been a really large experiment in the Arctic. An icebreaker went up there, was frozen into the ice there for a year, and lots of observations of the atmosphere, the snow, the sea ice, and the ocean, and also distributed horizontal network, and biological measurements, and aerosols, and lots of different things were measured at one place for the whole year. And wintertime data in the Arctic, in the high Arctic, is really scarce. The previous experiment like this was in 96, 97, I think, so it's a long time ago. So having this concentrated effort with many nations going together and doing this together to really make a comprehensive data set where we observe all the things that we need to study the couple system is really a good step forward. And I think we need to do more of that when we go into the future, having more selective, research question-driven missions where we go together as a society to try to find the best way of observing this, to capture something which is not happening every time and everywhere, to focus our efforts. I think that would be a good way to forward. And combine that with long-term standing stations, like the one at Östergarnsholm, and there are a few around the Arctic as well, which has long time series, where we can do statistical measurements, observations, and look at different regimes and so on, to try to understand problems in our models a lot better. And there we can become really technical and talk about data exchange. And Linus said that he wants to have easy access to observational data. And that's something we worked on in this project, to make data accessible, observational data accessible for modelers to be able to do a good evaluation of them.
Okay, thank you, Gunilla. Any comments from Anna concerning what they've said?
Just one. I have one question, and this is more because in society there is a big belief in new data methods, so artificial intelligence, machine learning, that will solve the problem. So will it? Is that the solution to the weather forecast or the climate models? That's what I'm curious what you think about.
One way to see it is that what we have done for decades in the data simulation is actually in one way machine learning. So it's a word that is used a lot now, but it's statistical techniques that we have been using for a long time. But then I think finding erroneous observations and odd patterns and see what the observations that we should not use in the data simulation, that quality control we can improve with these new or newish methods.
Yes, I think we can use these methods to learn a lot about the data we have and so on, but we should always remember that these techniques can only do things within the data frame, within the data that has covered. And as we have a changing world, and it changes when we go into more and more climate change, that cannot be predicted by machine learning, because it cannot do things without what has been observed before or modeled before. So I think that's doubtful, but there are a lot of other things we can do with it.
Yeah, I can just fill into that. I also think there are a lot of things we can really learn. We have used the techniques for long times in some sense, but also that field is improving, and there are things happening within the artificial intelligence, etc. And I'm not the one to talk about that, but of course in a climate change impact way also there are a lot of other data that can be used as well. So it's not just the meteorological and climatological data, but also how it relates to different impacts. And I think that's maybe one of the fields where we can have most benefit from it.
Okay, thank you. Now I think the auditorium are screaming for questions, isn't it so? Do you have any questions? Who wants first? Mikael?
So I was thinking about Arctic amplification. It's not the same over the whole Central Arctic. It's larger in certain areas. Could you comment on the observation in those areas?
Please repeat the question.
Yes. So the question was about that the Arctic amplification is homogeneous, not homogeneous over the Arctic, and there are certain regions where it's much larger than others. And it turns out to be the largest region is the region where we know that the sea ice have retreated. So that's part of it, and that's like Barents Sea and this part of on this side, sort of. But it's very high as well in the more towards the Siberian Sea and outside of Siberia, and there we have the least data and the least coverage there. So I think there are issues there with the observations as well. But we can't go back and take more observations, of course. But we need to understand the processes better, so the models are better there.
Thank you. Any questions from here? Yes, please.
Continuing in the same direction concerning the, say, feedback mechanisms, especially the dramatic feedback mechanism, when I think of, say, ice sheet collapse, then you will have parameters that go probably well beyond where you are at the moment. So how do you work with that? Because current observations won't help, I guess.
That's a really tricky one because
Please
repeat the question. Yes. So the question was for me, or yes. So what happens with like if we get unstable ice sheets and things are happening which are much more rapidly than we have observed before? And of course, I think that we are pretty good with the models that we have to look at states that are close to what we have observed so far. But when we go beyond that, it's much harder. And we need to know more about the physics and what's going on there to be able to capture these things. And Antarctica and the research there and how it's destabilizing from ocean processes under, there is a really lack of observations, really lack of modeling knowledge of how we should treat this. And I think those are really uncertain things that we should invest and try to understand a lot better.
Thank you. Johan?
Yes, I guess this is for all of you. So today is a lot about long observational records. This important observational network that you're discussing, is it becoming better or is it degrading currently? And where do you see that it goes into the future?
Who would like to answer and repeat his question?
Okay, so the question was if the observational network kind of more globally, long-term records, or if it's degrading or if it's becoming better. I guess that's what the question was about. I can first of all very quickly say that I really don't know on a global scale. It depends on what kind of observations we are talking about, of course. The amount of remote sensing data is getting more and more, and you get more satellite products. And if they are handled in the good way, you can create long-term climatologies that are relatively homogeneous over time, and that has been done. For instance, there is now a 40-year climatology for clouds from SMHI Global that has been compiled from different satellites over different generations, which is more or less homogeneous in a way. So there are improvements in some data sets. But then when we get into data sets like Uppsala, and there are not so many of them, of course, but also all other gridded stations and synoptic stations and data stations, I don't have the full picture here, and we should talk to someone else about it. But I guess the picture is probably quite different in different parts of the world, I guess, depending on resources. In some countries and some places, there are really still big lacks and gaps, and there are even white areas on the global map if you look at some parts of the different continents. And in other places it's getting better, and then yet again you can have deteriorations in some places. We can also look at data like for Sweden, for instance, where we have a lot of data. We have a lot of information in the archives at SMHI, and some of these data are not even digitized yet, so they are sitting there waiting for you or someone else to dig into them and really start working on them. So there are still amounts of data, and these are now for the climatological context, and that could be used potentially, but it requires also I would say some kind of centralized resources around it, and also the long-term perspective. We also got the audience from the audience here before. I think he left now on the long-term continuation of the Uppsala series, how that can be handled, and I don't think that's handled in a good way in a global sense. But that's my perspective.
And just to fill in, so we haven't touched upon much here. the reanalysis as a tool to understand the past climate, and is very widely used. So one you use the data simulation use daily for the weather forecast, but look at past dates. So we currently go back starting around 1950 and so on. But the quality of such product is of course dependent on the number of observation that goes in. So if I use reanalysis data, one need to be aware of the kind of observations that have been going into these products. And if for reanalysis going back to the 19th century, when not much observations are there, then it's largely just a model-generated climatology.
And just to think, we've talked about 3 different types of data, and I think there is a competition of resources to have these 3 kinds of data. And I think we need, as a community, to be really clever and try to guide where we get the most for the money, so to say, to understand the problems that we want to study. But it's really good, really important to have long records, a good coverage, but also having this process level data so we can really understand the processes to build the models better, because then the reanalysis will be better and we can trust it more to look at more processes and the climate models as well. So that's the belief that if we improve the models, then we will improve, and we need observations to improve the models, and then we can use the models more.
Yes, and I agree with what has been said here, but I am under the impression that we get better, so we get more data and we get more high quality data. Not as much and as good as we want to or think we need, but I think there is an increase and improvement on the amount of data.
Okay, thank you. Then I have a last question. Assuming that Anders Celsius is standing here in front of you, in front of us all, and he has been living today and seen what happens with the global temperature increase of today and so on, with the Arctic and so on. What do you think his reaction would be? What he will do? Will he continue collecting data, as I think you think? Or will he stand on the Mynttorget every Friday? That's the question. Somebody that wants to answer.
Yeah, after hearing Anders talk, then I got pretty certain that Anders Celsius would be constructing satellite instruments these days. To being on that edge of technology to find new clever ways to make measurements.
Yes, my thoughts went in the same direction. From my vision that I got from your talk about how he was, I think he was really curiosity driven, and I think he would be really wanting to understand why and where and so on, finding out different ways of observing it to be able to answer the question.
Yeah, he was a indeed curiosity-driven guy, as you said, and but I think and also your very last quotation from him also when he said that he was not worrying too much since he didn't have any kids. So maybe he would not be worrying too much about the ongoing environmental problems. I don't know. I have no idea. Of course, it will be a different situation for him, but he would definitely be there working with them in some way, measurements or modeling or something. I don't know, but he would be there working with it for sure.
And he would charm the people with the money to get it done.
Yes, just one comment, because I've heard, or I got comments myself that people say, now we know enough about climate, now it's time to act. And I think we as people, we need to be able to have 2 thoughts in the mind at the same time. Yes, we need to do something about the changing climate, but we don't know enough. We need to know more. So we should not stop investigating and understanding the surroundings and the changes. I think that's really important from my perspective.
Okay, thank you. Now it's time for presents. Still there. Please still there. This is the most tricky of this seminar. So, please, thank you. Okay. We like to thank all persons that have taken part of the work that has been carried out for making this celebration day possible. Johan and Eric and so on. I can't even all the names. A special thanks. Yeah. A special thanks to the participants that have given presentations and sitting in the panel today. And all of you sitting here and also listen. Thank you for taking part of these celebrations of the 300 years of weather measurements here in Uppsala, honoring under Celsius. And after the symposium, we offer some light refreshments in the seminar hall direct to the right. So, thank you very much.